Well, Mr. Einstein hier ist zurückgekommen. I see Mr. Schwanson talked too long again, so he ran out of time for the other video to put number 14. So here you see, he has drawn a very nice diagram. Herr Einstein, but my turn. My turn. Yeah, okay. Bye, kids. Turning over to Mr. Schwanson now. Oh boy. Anyway, so it is impossible in my mind to do number 14 if you don't sketch out a diagram so you can keep straight in your mind what's going on. So we're asked to calculate the distance between the center of the Earth and the center of the Moon, where the force of gravity will be equal from the Earth will be equal to the force exerted by the Moon. So if you sketch out the diagram here, the Earth to the Moon, we know the distance from the Earth to the Moon, that's given on the front page as this many meters. So somewhere in between will be the object. Well, we kind of know it has to be closer to the Moon because the Moon has so much less mass than the Earth, so I put it there, but you don't really have to. And for some reason here I use capital R for distance instead of small r. Oh, this should be r to the Moon. And kind of sketched out defining what is what. So you need to refer to this diagram as I work through the problem or you're going to get lost. All right, so starting down here, we know the gravitational forces are equal. So from this equation, the force will be of gravity exerted by the Moon will be equal to the force of gravity exerted on the object by the Earth. Or, using this equation, just put them in here. Here's the force of gravity exerted by the Moon on the object, the force of gravity exerted by the Earth on the object, and they are equal to each other because the forces are equal. All right, so going from this one here, I've transferred it to the other paper. I guess I forgot something. So if you look at this, the G's, since they're on each side of the equal sign, will cancel each other out. They divide out. Same thing with the mass of the object. You don't even need to use that. And we're left with this expression that the mass of the Moon divided by the distance from the object to the Moon will be equal to the mass of the Earth divided by the distance of the object from the Earth. All right, so that's starting here. And there's more than one way to work it, but I worked it this way. So I'm solving for the distance from the object to the Earth, or r sub e squared. Just rearranging this equation, the r comes up here, and we end up with this expression. The radius, or the distance to the Earth squared, will be equal to the mass of the Earth times the distance to the Moon squared divided by the mass of the Moon. Or putting the numbers in, 5.98 times 10 to the 24th kilograms, the mass of the Earth divided by the mass of the Moon, times the radius squared of the Moon. Our kilograms cancel out, one in the numerator, one in the denominator, and we're left with a radius, or the distance to the Earth squared will be equal to 81.25 times the distance from the object to the Moon squared. Just doing the math here for you, taking square root to get the distance to the Earth instead of distance to the Earth squared. I get that the distance from the object to the Earth is 9.01 times the distance from the object to the Moon. Now we know from the little diagram that the distance from the object to the Moon, to the Earth, plus the distance of the object from the Moon's center of mass will be equal to the distance between the center of masses of the Earth and Moon, which is given on the data sheet. So those two added together will equal the distance from the Earth to the Moon's center of mass. And we know, so the distance to the Earth is 9.01 times the distance to the Moon, so we just take that value for the distance of the Earth to the Earth and plug it in there. So this number, 9.01 times the distance to the Moon plus the distance to the Moon, equals that distance, or 9.01 plus 1, rm, means it's 10.01 times the distance to the moon equals that number from the front sheet. So I figured out the math here. That means the distance from the object to the moon is 3.836 times 10 to the 7th meters. We know from what we solved up here that the distance to the Earth is 9 times the distance to the moon. So the distance to the Earth equals 9.01 times the distance to the moon. So that's this number. You just multiply that number by 9.01 and you get 3.46 times 10 to the 8th meters. Or you could do the addition and subtraction the way I did it on here. Taking the distance from the Earth to the moon, subtracting the distance from the object to the moon, you get the same number. Boy, Mr. Einstein, what do you think? Was that fun? Well, yes, it was sehr fun, very fun, as we say in Germany. And now, Mr. Schwanson, I think that your students will think you're a big dork for having me on here and talking stupid like this. Well, I can't help it. And, by the way, what is all that stuff, silly stuff about the why is a duck thing? I still don't get it. Would you explain it to me? Well, yes. The way it works, I've been meaning to explain this to my students. The real meaning is that when you go to the